Welcome to session 2 of the Generalized Linear Models lecture. And here we'll now extend it into the log likelihood. So we're going to look again at where AY is just Y and theta is a scalar parameter. And so the log likelihood, or LLI, is just simply yi times that function b of the parameters plus c of the parameters and plus d of yi. And of what we had seen in the previous lecture is the mean is equal to minus the first derivative of c divided by the first derivative of b. And the variance is this function of the second derivative of b times the first derivative of c minus the second derivative of c times the first derivative of b divided by the first derivative cubed. Now, here's where we get into a part of the generalized linear model that turns it into something of great interest in the sense that it is going to be expressed as a function of a linear combination of explanatory variables. So if we think of a function g that connects the mean of the variable with this linear combination of x's, then g is called the link function. And it links the mean to this linear combination, which we will also denote as a to I sometimes. So the inverse of that, h, is just simply g inverse, and we can think of the h function or the inverse link function as connecting x beta to the mean. Now, if we consider the log likelihood, it is the log likelihood of each component or observation summed across all the observations in the data set. So we're summing across I, and since, again, we are looking at this combination up here, right there, we will take the derivatives and sum on that. So first of all, the likelihood is the sum of the first term yi times that capital B of theta plus the sum across the c's and the sum across the yi's. If we take the derivative of the likelihood with respect to beta, remember now beta is embedded in our linear combination right here, then what we are looking at is, for the term, we're looking at the derivative of the log likelihood with respect to the theta parameter times the derivative of the theta with respect to the mean times the derivative of the mean with respect to beta. We're just applying the chain rule. Now, looking closely, yi times beta plus c, beta 1, the first derivative of the b, plus the first derivative of c, beta 1, is our derivative in terms of theta, which if we were to pull the b function out, which means it would end up with this being divided by b, right? And negative of that divided by b is equal to mu, so what we end up with is the first derivative likelihood function is the first derivative of the b function times yi minus mu I, yi minus its mean. Moreover, if we kind of take the strategy of considering the derivative of theta with respect to mu, that's this part up here, is 1 over the inverse of the derivative of mu with respect to theta, we can look at the derivative of mu with respect to theta, and if we look at that above, we can see that it breaks down into the negative of the second derivative of c over b1 plus c1 over the second derivative of b2 divided by b1 squared. A little bit of algebra, pulling b1 out, shows that that's the same thing as b1, the first derivative of that function b, times the variance of yi. So if we take the inverse of that to get our d theta d mu, we have it as the inverse of the first derivative of b times the variance of yi. So if we put the parts together, we have the derivative with respect to beta is the sum of the b1 yi minus mu I, and here I'm going to kind of do this a little strange because I'm going to kind of convert away from the matrix notation just to see what it is, this inverse. And we've got this first derivative of b1 divided by the variance of the first derivative times the variance of yi, the denominator here, times d mu d beta. So the reason to point it out that way is just to note that this is canceling. The b1's canceling. So really what we have is our y minus mu. Right, that's up here. And then back again, allowing us to be able to do this later on in a matrix notation. We'll let our variance y be expressed just directly as the inverse of v. And then our d mu is our d mu. But d mu d beta is the same as d mu d eta times d eta d beta. And eta is our x. Remember, eta is equal to x beta. So that is d mu d eta, which is d mu with respect to x beta as a total linear combination, times the derivative of x beta with respect to beta, and that's just the corresponding x. So now if we plug that in, we have the summation across the observations of x times d mu d eta, where eta is just that linear combination of x beta, times the inverse of the variance, times yi minus mu, and we set that equal to 0, and we solve, right? However, we can go one step further, and we can say that for the variance equal to some function of parameters times some function of the mean, and remember that in preceding sections of this lecture, we had talked about the variance being a function of the mean. So if we can express it as a function of the mean where it is some scale of a function of the mean, and we can further write this as our x times d mu d eta times this function of the mean inverse, allowing this inverse to just come on underneath my y minus mu, and I can have y minus mu divided by that scale factor times this inverse of this function of the mean times the derivative of the mean with respect to x beta, which I'm calling eta, times x. Set that equal to 0. These are the estimating equations for the generalized linear model. Now we derive this from characteristics of the exponential family as maximum likelihood. And therefore, for the exponential family, this is an efficient estimator. We can, therefore, that being a maximum likelihood estimator, we can use the likelihood ratio tests, AICs, BICs, etc. That basically follows from maximum likelihood. What is interesting, though, is that the estimating equations is a function only of the first two moments, the mean and the variance, which led Wedenberg to suggest using the same estimating equations regardless of whether the distribution is exponential or not, and what was termed quasi-maximum likelihood. However, we needn't even go to that approach to determine this. We can go back to our lectures on generalized method of moments, and we can note that if we were to look at y minus mu beta as our kind of error term, here is a inverse of a variance matrix, or you can just think of it as our positive definite matrix, y minus mu. This is the form of the quadratics that we were looking at in the generalized method of moments. But if we take the derivative of that, what do we get? We get our y minus mu as with respect to beta, the inverse of that variance function, the derivative of mu with respect to beta, times the -2, but if we set it equal to 0, -2 doesn't matter, and it turns out to be exactly this, which is generalized method of moments estimator, and it really is just essentially what we had above. So we can think of it as the generalized method of moments estimator, and so consequently, when we move away from the maximum likelihood, we think of what are the characteristics going to be of this quasi-maximum likelihood, because we're no longer in an exponential function. Well, it's going to follow the generalized method of moments lecture in terms of its properties. So it's going to be consistent for any positive definite matrix V, but best if it's that variance function. It's going to be asymptotically normal. It's going to, our asymptotic distribution will be based on this limiting distribution, where we can estimate our theta squared as a function of two different matrices. One is a function of is the Hessian, right? It's the derivative of Q, where Q is the derivative likelihood, so it is actually the second derivative of our estimated function, actually. It doesn't have to be the likelihood function because we're doing generalized method of moments, but it's therefore the derivative of the derivative, so it's a second derivative matrix. And J is our outer product of the first derivatives, right? If this is Q here in our estimated equation, it's the first derivative, so we're taking the outer product. So we have our sandwich estimator that we're familiar with from the previous lectures. So let's take an example. Let's suppose that the expected value of y is e to the x beta. So the link function is the log link, right? Because the log of the mean is equal to x beta. Let's say the variance is equal to some scale. That was that alpha of phi is going to be e to the phi times the mean, e to the x beta, right? Q is my xi times e to the x beta times that variance inverse times y minus e to the x beta. We're going to set that equal to 0. Do a little bit of algebra here, taking into account these two quantities, and this turns out to be xi times this yi minus e to the x beta divided by e to the phi. Set that equal to 0. Now this is a setup for almost a Poisson. In other words, a Poisson would have the expected value of y equal to the variance, which would make e to the phi equal to 1. So this would be our Poisson regression, or Poisson estimation in a generalized linear model approach. So if instead of using this for the Poisson, which has the e to the phi equal to 1, we were to use these estimated equations, it would allow for essentially an adjustment of the variance. It would allow for a variance inflated Poisson, because it would allow for estimating an inflation factor on the variance, and that's what that e to the phi is. So one of the advantages of taking this approach is that you can take what would otherwise be a stricter specification and work with one that allows a little bit more freedom in terms of some of the parameters. In this case, it allows for the variance not to be equal to the mean. So this ends the second session of the generalized linear model lecture.